4 and 5 are in series. In this branch, R2 and 3 are in series, but the two branches are in parallel with each other. We have to know and understand when to use the series circuit rules and when to use the parallel circuit rules. One of the key things is that we always start solving and reducing the circuit from the right hand side when we're trying to reduce and find the total resistance. So one way that we could do this is start over here with our resistances. These two resistances are in series, and so we know for this branch we have 40 ohms, 10 ohms plus 30 ohms. And for this branch we have 4 ohms plus 6 ohms, or 10 ohms. So together we have to solve these by using our parallel circuit rule. So first we reduced them down to one resistor within the branch, so that we got the 40 in this and the 10 in this. And then to find our total for this, we take the inverse of 10 and the inverse of 40 and add them together and take the inverse of that answer, and that'll give us the resistance for 2, 3, 4, and 5, all of these resistances. And that actually works out to be 8 ohms. And now I have to take that 8 ohms, and it's in series with R1, so I just add it, the 8 and 2, and over here for my total I would end up with 10 ohms of resistance. Once I get that, I can go 24 times 10 and give me 240 volts for a source. Now another thing that I could have done is over here I have enough numbers that I could find the voltage of R4. It's 4.8 times 10, or 48 volts. And R5 is 4.8 amps times 30 ohms, and that will give me 144 volts. Together, those two voltages are 192 volts. So these two resistors are 192 volts. Now they're in parallel with R2 and 3. So that means these two resistors also have to be 192 volts. If I was to draw an equivalent T for this branch, I would have 192 volts, and because the two resistors are in series, that 192 volts is shared between resistor R2 and R3, and the amount of resistance that R2 and R3 offer in that branch is the 4 plus 6, or 10 ohms of resistance. So the total voltage from the top of that branch to the bottom of the branch is 192 volts. The total resistance from the top of the branch to the bottom of the branch is 10 ohms. And from that, I can figure out that there's 19.2 amps flowing down this circuit. So in here, 19.2 amps is the current flowing through R2, and it's also the current flowing through R3, because in a series circuit, which is the middle of this branch is, the same current will flow through R2 as flows through R3. At this junction or node right here, if I had 4.8 amps flowing around through that second branch and a 19.2 amps flowing down the first branch, that would mean that I would need 24 amps flowing out of R1. So 24 amps comes into this junction, 19.2 heads down the first branch, 4.8 head around to the second branch, and when it gets back over here, of course, joins up at this junction, it joins back up from those two branches, and you have 24 amps returning back to your source. So over here at R1, when I multiply the 24 and the 2, I end up with 48 volts. And we've kind of solved all of the circuit. We can double check a few things. So around any closed loop, let's take this one. I have a source of 240 volts. So all of the voltages in that closed loop add up to that 240. So I had 48. Oops, we didn't quite finish this little job here. So let's go back. 19.2 times 4 ohms gave us 76.8 volts for R2. And when I take 19.2 times 6, I end up with a 115.2 volts at R3. So let's go back and figure out if we have a closed loop that adds up to 240 volts. At this one I had 48, at this one I had 76.8, and at this one I had 115.2, and when I add all of those up, I do get 240 volts. So that closed loop works. Let's check the next closed loop, because it also has to add up. So I start out with 240 volts. I have a 48 volt drop at R1, and then over here I have another 48 volt drop, and then at R5 I have a 144 volt drop. When I add those three up, this one, and this one, makes that outer loop, and I see that it does add up to 240. And we're done. Thanks.